All right, next up for our reaction types, we have decomposition reactions, which if you can see, I start with one couple. That is the only reactant I have. And that breakup happens to where my products are two single people. Most commonly, I will have you write a decomposition reaction for a simple ionic compound, right? Which is why on my slide, I have an A-B compound, half colored red and half colored blue, right? That means when they split up, they will become single metal and a single nonmetal. There are other decomposition reactions where you could, break up into two or more. Some are a lot, are not just the simple breaking up of an ionic compound, but those are the ones that I will have you guys be able to predict. Okay, and that's what we'll be practicing here. It says a decomposition reaction is a reaction where a compound breaks down into two or more products. Now, stuff does not usually just spontaneously decompose. Usually it takes a lot of time if something does spontaneously decompose. But a lot of times heat or electrolysis is usually necessary. So in terms of our couples, if this is a couple breaking up, usually a big fight or a conflict or a little heat is what causes a breakup to happen. So here's an example here of an ionic compound breaking up or decomposing. It says a compound can break up into two elements. So here I've got molten sodium chloride is electrolyzed. Electrolyzed means electricity is flown through the sample is pushed through the sample that causes actually the ionic compound to break apart. So I notice for this guy, I have got a metal sodium and the non-metal chlorine. So this is sodium chloride, and it breaks up into a metal plain old sodium and then plain old chlorine. And you are already like, the numbers, what is not making sense here? Okay, remember our diatomics. In fact, I'm gonna write my diatomics up here at the top again. Diatomics, which are my Hofbrinkels. H2O2 F2 Hof, Br2 I2 N2 Cl2. All of those guys, if from the breakup they are involved, they will always get a subscript of 2, okay? But we are still of the mentality of dropping subscripts from the reactant side. So we will rewrite that again because it is important to us. Drop all subscripts from previous reactants. Yes? Okay. Amazing. So there is an ability for you guys, if I were to give you not an ionic compound, if I gave you a covalent compound and I ask you to decompose them, you could do that pretty easily. That's more difficult to form a covalent compound because I would have to let you know in the compound how many of each element you have. But you could break up a covalent compound. There are some examples down here at the bottom, right? We have hydrogen peroxide. That's totally covalent. All that means is I would just still be writing the two elements from that original compound as single people, which is nothing that I need more information from. Okay, so let's crank on through and see what we got going on here. So if I just were to give you this and you were like, I do not know what to do with this. Y'all, the starting thing I've given you is a couple. There ain't nothing else for you to do with that couple besides break them up. So you will know you have a decomposition reaction coming when you see this, right? You can also identify whether it's, ionic or covalent. Not like that actually really matters, but we like to get in the habit of doing that anyway because it makes us better chemists. But mercury is a metal and oxygen is a non-metal. And in fact, I'm going to switch down to purely the document camera lecture so we can kind of get going this way. So that's totally an ionic compound. We love that, right? H2O, hydrogen, a metal, a non-metal. We got a covalent. Two non-metals. We got a covalent. The next one, we have lead iodide, specifically lead 1 iodide. Y'all are like, oh my gosh, she's naming some things. I sure am. And then we have, this is called hydrogen peroxide, but I would be fine if you called this dihydrogen dioxide. I would understand that, no big deal. Covalent. I can even move down here and see when I got the names. I'm just looking if I got metals or nonmetals. I got nitrogen and oxygen. That's a covalent compound. Oh man, here we go again. I'm gonna have to make you write my formulas for me for this ionic compound. Iron 2 nitride. We have a metal and a nonmetal, so that's ionic as well. And then my last example is aluminum chloride. Aluminum is a metal, chlorine is a nonmetal, so that is an ionic compound. So you can break apart pretty much anybody I give you. All you have to do is just write them as single people. Do not bring subscripts over. Write them as is, fresh and free, just their element symbol unless they are a diatomic. So we are super excited about this. These are super fun. I love the decomposition reactions. Okay, first one. Mercury, is he diatomic? No, he is not. So guess what? When Mercury is free, he's free. No subscripts for me, right? And then my second guy, my second single and free guy is oxygen. Woo, he's free, except for he is a diatomic. So even when he is in the freedom stage of his life, he comes in twos. Okay, we know the last step of every single writing reaction problem is to balance at the end. It looks like the fact that this guy is diatomic and is a single person comes in twos means I have to put a 2 on the mercury 2 oxide side, and then that means I would have to put a 2 in front of my single mercury on the product side. Amazing. Okay, and once again I see just, you know, my metal and my non-metal. You guys do not have to keep using the red and blue bit if it is helpful, especially for the purpose of watching a video on how to write these things. I think that that could be useful. Okay, cool. Amazing. So they are in a couple. I noticed I got a 2 underneath hydrogen. That sounds good, but if I am getting out of a bad relationship, I'm going to leave the baggage from my bad relationship over there, meaning we drop our subscripts. Okay, we are free. No subscripts from me unless I am a diatomic, which oddly enough, both hydrogen and oxygen are diatomics. But hydrogen on this side gets a 2, not because he came with a 2 over there. That's because that's what he always has when he is in his single form. Balancing at the end, it looks like I need to put a 2 in front of water over here, right? To give me the 2 oxygens that I have on the product side, which then would make me have 4 total hydrogens on my water side. So I would put a 2 there. Good stuff. So here was 2 nonmetals breaking apart from a covalent compound. Okay, we got lead 1 iodide. Break them up. If there were any subscripts, get them out of here. We're free. We're free. We got lead, not diatomic. Looks good to me. Iodine. Oh, he's diatomic. Give him a 2. Okay. Now we are going to balance at the very end. Let's see. 2 iodines over here, which means I need 2 on the reactant side, which then means I will need 2 leads on that product side. Looking good. See, we're moving a little bit faster. Those diatomics, man, they really mix some things up. We gotta be aware of them. That is for sure. So this is H2O2. It's hydrogen peroxide. You would call it dihydrogen dioxide. It's fine. Break them apart. Hydrogen, oxygen. We're free. We're free. Unless you're diatomic, you get a 2, which they are both diatomics. I know. I love this for us. Okay. Balance at the end. It looks like, yo, we're already balanced. I have 2 hydrogens on both sides and 2 oxygens on both sides. So that looks amazing for us. That's not too terrible, right, you guys? Like, we can do the hard things. Get rid of those subscripts from the reactant side. That's a bad relationship if they are now breaking up, right? Okay. But now on this section here, I'm like, well, you need to first write for me the couple, and then you will break them up. And you're like, oh my gosh, this is so annoying. This is why identifying ionic or covalent is so super important. Because when it comes to writing ionic formulas, I got to set up the crisscross, right? Based on their charges, right? How many ratios of each ion I have. For my covalent, like the first one here, it just tells you how many of each guy I have, right? Okay, so let's do this. Covalent, I have 2 nitrogens and I have 2 oxygens. Okay, that was apparently a bad breakup, so they gonna be free, right? Unless they are diatomic, and y'all, both of these guys are nitrogen and oxygen. So it is by coincidence that they still retain their 2s on the product side, not because it got dragged over, but just because as single elements, they are diatomics. So I do not have to balance. I have the same number of nitrogens and oxygens on both sides of my reaction equation. Okay, now the last three are ionics. I must have a crisscross, which means I need to know what the charges is of both of these elements, so I can figure out what the original formula is. You're like, why does it matter if they just gonna be free on the product side? Well, I gotta balance, you guys. So whatever the original couple formula is does matter in terms of the number of each ion of each I have. So that IV means this lead has a plus, or this tin has a +4 charge. +4, sorry guys, +4. And sulfide, IDE ending means plain old sulfur. He's got a -2 charge. And in fact, since this is a little bit of a trickier crisscross, I'm going to write this off to the side. So we know that tin has a +4 charge, right? And sulfur has a -2 charge. That is what we discussed, right? Well, the ratio, if I were to simply crisscross, would be technically SN2, S4. But a 2-to-2 ratio, or a 2-to-4 ratio, we can reduce down to a 1-to-2 ratio. So that's what we'll do here. So tin 4 sulfide is actually going to look like SnS2, which now introduces the concept of remembering that I cannot reduce down covalence, okay? So if I have dinitrogen dioxide, there must be, because they're physically connected, I must have 2 nitrogens for every 2 oxygens. But my ionics, it is just a ratio of how many of each type of ion I have in a just billions of ions wide crystal lattice structure, right? Okay, so now I'm gonna make everybody free. We're free. That was the hardest part, is just writing the formula. Now we're gonna be free, right? So we got tin. Tin totally is not a diatomic, right? Sulfur is also not a diatomic, right? So none of those original subscripts get brought over. Nobody is diatomic, so that looks good, except now I just need to balance at the end. And my balancing, I'm going to put a 2 in front of sulfur on the product side. Amazing. So that's the decomposition of tin 4 sulfide. We're now ready to do another decomposition. Iron 2, that means my iron has a +2 charge. And then nitride. It's not nitrite, it's not nitrate, it's not one of my polyatomic ions. Nitride is plain old nitrogen, which means nitrogen has a -3 charge, right? So if I were to set up a crisscross, and I will take the time on this video to do this, because if we are watching this video, we may need some more help. I may need some more modeling on how I'm getting these formulas for my reactant of iron 2 nitride. Okay, this means that it will be a 3 iron to every 2 nitrogen ratio to neutralize that charge, and that's what I mean when I say crisscross. So I'm going to say Fe3N2, right? Bad breakup is happening. We be free, I'm free, get out of here, look at me, I'm so free. No subscripts, come with me. I'm rhyming a lot today, that's really fun. Woo! Unless I'm a diatomic. Who is diatomic here? Not iron, but nitrogen definitely is, so he comes in 2. Coincidence purely that he had a 2 on the other side. So now when you get to balancing, the only person who needs help with the balancing is the iron, who is free. And there are 3 of them. Man, this is rhyming. I'm losing it today, you guys. What is going on? Okay, last one. Aluminum chloride. Aluminum chloride. What's the formula for aluminum chloride? Aluminum, I got a +3 charge. Chloride is plain old chlorine. So setting up the crisscross, Al with a +3 charge and chlorine with a -1. So I will have a 1-to-3 ratio. So aluminum chloride will be AlCl3. They break apart. Woo, gonna be free. Get rid of the subscripts. Did not like that previous relationship. Do not want that baggage. Aluminum is totally not a diatomic, but chlorine is. So when he's free and single, he comes in 2s. You're like, oh, I'm nervous. That is okay. I just need to balance my chlorines. I got an even-odd situation. We know when we are even-odd situation, we know when we have 3 chlorines on one side and 2 on the other. I like to double that side that we at 3, because then it makes things a lot easier. So yes, that changes my aluminums to 2. So I put 2 on the product side. But then that'll give me 6 total chlorines on the reactant side, which then I can fix over here by putting a 3 to give me 6 total chlorines on the product side. So what we've done here, you guys, is we just made each other free. Just like my synthesis, guys, the theme is to not bring that baggage from the reactant side. No subscripts, no thank you. I have to create my own subscripts depending on if they are one of my diatomics. If they are not a diatomic, then he gets nothing on him. If we are asked to write the formula for our reactant, okay, we will need to know our nomenclature rules on how to write formulas by identifying whether we have a covalent or an ionic one, and then applying my crisscross for my ionic, or looking at my prefixes for my covalent stuff. But always balancing at the end. We have tackled some decomposition reactions, which I'm pumped about.